morning.
Hi, Jen.
Hello. I'm good. How are you doing?
Pretty good.
Good. I know you're not going anywhere for reading week, but hopefully it's going well.
Oh, it's fine.
Good. Okay.
Yeah, just fine. Yeah.
Good.
So, what would you like to talk about today?
Yeah, just, so I'm studying and I'm just, like, I came back to school and I was working on an English degree, and so now I'm coming back to math. Like, I took a lot of calculus in college, like, many years ago, but so it's just kind of overwhelming, like, what to study. Yeah, like how thorough to be on the like lecture slides versus like all the textbook chapters. I love that you gave us kind of like an exhaustive amount of textbook chapters, but I'm having a hard time like parsing because sometimes the people writing the books will go off on like a topic that we didn't cover, but I'm like, well, it's tangentially related. I'm not sure if he exactly wants us to care about it. So stuff like that.
Yeah, it's a good question. I think that the simple answer to that is you should focus mainly on the things that we covered in lecture.
Okay.
That's like the meat and potatoes of
Okay,
the
it does.
content.
Okay.
And then it's true, I did give a lot of, for some topics, I gave quite a lot of readings to do. And I mean, I would say again, if it was never mentioned in any of the lectures, and if it was never mentioned in any of the homeworks, then it's pretty unlikely that it will be on an exam.
Okay, that's great to know. Okay.
Yeah, like an example is the material on effect sizes.
Okay.
I mentioned, I don't remember which lecture I mentioned effect sizes in the slides, just sort of very briefly. I said, this relates to effect sizes.
Yeah.
I think I gave a pointer to the chapter, and I said, we're not going to cover it in lecture, but you should read about it. That's an example of something that might be on an exam.
Yeah.
That we didn't like.
Oh, yeah, because you did mention it. Okay, that makes a lot of
So
sense.
I think you should think about it like that. I'm not going to be tricky or mean or surprise anyone.
Okay.
Yeah.
In the confidence intervals, I know that was kind of a thing too. Like we covered it, but we didn't cover it. Like, how do you know? Anyway, I don't know if that's an inappropriate question, but should I be studying that?
Jeez, I'm trying to think. Is there a question on confidence intervals? There might be. Yeah, there might be.
Sure,
that's a question on what they mean.
Oh, okay.
Like not how to calculate them necessarily, but like what they mean. Because remember, it's that complicated thing, right? It's not exactly 95% confidence that.
Oh, that's so tricky. I will write that on the cheat sheet the way that you word it, because you word it really well. Okay.
Yeah. That whole thing. Remember, I showed this slide of that kind of illustrated what you want it to mean is, well, there's 95% chance that the population mean falls between these two values, but it's not exactly that, right? This crazy thing where if you were to run the experiment 100 times and each time compute a 95% confidence interval, then 95 of those 100 confidence intervals would contain the true population mean and 5 wouldn't. And you don't know which ones.
Yeah, it's wild.
So there might be I don't remember. There might be a question that kind of said that.
That's fair. I mean, that's pretty important. Okay, that makes sense.
It's slightly tricky, but that's kind of the far end of how tricky and how beyond the lectures things go.
Okay, that gives a lot better sense of it.
So I would say really concentrate on the lecture slides and the concepts that are covered there.
Okay, I could do that.
Try the exams really to ask questions that probe the understanding of the concepts.
Okay, and I took a class through the statistics department. It was an anti-requisite for the first part of this course. It just worked out that way, but she kind of got bogged down, didn't really finish the course properly. So we had 1 week on T-tests and F-tests, so I'm just not very solid about what exactly is going on. Do the names exactly matter? Is there a one-to-one correspondence between it being a T-test and it being one thing, or is it more of a concept?
Well, I think the way I would answer it, the T-test is fairly specific.
Okay.
That it involves involves computing this quantity called T.
Yeah, okay.
Which is like, if it's a two-sample t-test, it computes like the difference between means of each group, and then you divide by, I don't remember what,
Okay.
something related to the standard deviation.
Okay.
So in that sense, it's a specific thing because the t statistic is a specific equation.
Okay, okay.
But the other way I would answer it is whether it's a t-test or an f-test, or a chi-square test, which we can cover in this course, but you might have heard about.
Yeah.
All of these tests share a common conceptual feature, which is that they're all null hypothesis significance tests.
Okay.
So
Okay.
they all involve the concept that we're taking a sample from the population, try to estimate something about the population, right? And the statistic we compute, whether it's a T or an F, it's something that ultimately it tells us kind of it relates to the p-value that we compute, which is sort of the probability that we could have observed a difference this big, a statistic, a t-value this big or an f-value this big in our sample if in the population there was actually no difference.
Okay. Oh, okay. So that's the same for every test. Okay.
Yeah,
Okay.
yeah, it's the same concept for all
Okay.
tests. You have a null hypothesis where basically everything is random, there's no difference between anything.
Yeah. Yeah. Okay.
And then you have an alternate hypothesis, which is that's not the case. There's a difference because my drug works.
Okay. Okay.
Because there's a sex difference in this phenomenon or whatever. And so the statistic that you compute, whether it's a T or an F, it kind of characterizes the largeness of the difference you observe in your sample in your experiment relative to the variability in the data that you have.
Can you just rephrase that sentence like in all different words? Because it kind of makes sense, it kind of doesn't. Can you just re-say that?
Yeah, so when you compute a T statistic or an F statistic, what it's trying to characterize in the same number is it's kind of characterizing how big of a difference you have in your sample relative to how variable your sample data are.
Oh, yeah. Okay. Okay. Because because if there's a difference, it's more different than the normal variability, kind of.
Yeah, that's right. Yeah, you kind of assume in the population there's a normal distribution of whatever it is. Height, weight, whatever it is. And so when you take a random sample from that population, you randomly pick people. Most of the time you're picking from the sort of lump of that distribution. Yeah. But sometimes you might pick a weird value that's either unusually small or unusually big. And depending on the breadth of that normal distribution in the population, the sample that you pick might also be more or less variable. So you can imagine if you take two random samples from a population and the samples have really different means. Really different averages, and their variability of each of those samples is really small, so the distribution of each sample is really tight around their means. You have a lot more confidence that there's a real difference than if you had two samples with the same difference in means, but very variable data.
Yeah, okay. That makes sense.
There was a slide, I don't remember which lecture it was, there was a slide where I tried to talk about that.
Okay, if you find it, that's great.
ANOVA. Oh yeah, here.
Okay.
Let me just quickly share my screen.
Oh yeah, that sounds great.
It's the ANOVA.
Oh, okay.
Remember that slide?
Yes. Yeah.
Yeah, so on the left is where you have three samples, group 1, group 2, and group 3, and the average value in each of those groups is different. Right? Group 1 is the lowest, group 2 is in the middle, and group 3 is the highest. And within each group, the data are fairly tightly clustered around their averages. And on the right, you have 3 other groups. And in fact, I designed these so that they have the same average values as the ones on the left. The average value of these yellow ones is the same as the average value of those yellow ones. But within each sample, there's a lot more variability.
Yeah, okay.
Right?
Okay.
So if I gave you these data, versus these data, and I said, what's happening here? Probably on the data on the left, you'd be much more confident that, well, yeah, those are actually different. If this is a placebo and this is drug number one, and this is what if you double the dosage or something, you'd be much more likely to say, oh yeah, I think that drug actually works. Whereas if I gave you these data, I don't know. I mean, yeah, the average is higher, but look how variable it is. Half of these green ones are, well, not half of them. A bunch of these green ones are even lower than some of the orange ones. So does the drug really work? I don't know. The data are so variable, I'm not very confident. And so whether it's a T statistic or, in this case, in an ANOVA, it will be an F statistic.
Okay.
It kind of trades off the difference between the average values, and it kind of normalizes those average value differences by how variable the data are within each group.
Oh.
And so the bigger the T or the bigger the F, the bigger the differences are relative to the variability within each group. So it's a very similar concept to effect size, but these statistics, T or F or chi-square, they relate to a p-value, a probability. And that p-value will tell you very specifically what's the probability I could have obtained differences in average value this big if there were actually no differences in the population and these three groups were randomly sampled from the same normal distribution.
And it calculates that based on the variability, and you want lower variability.
That's right, yeah.
Okay.
So if you imagine the null hypothesis for these groups on the left, the null hypothesis is I have one normal distribution.
Okay.
And I randomly pick 10 values, and they're group 1, and I randomly pick 10 more values, and they're group 2, and I randomly pick 10 more, and they end up in group 3. So what's the chance I could pick 10 random values from the left-hand side of this normal distribution, and then 10 values from the middle, and then 10 values that are all on the right? That's pretty unlikely if I'm really picking a...
Oh, okay. Right. That makes sense, because if it's the same normal curve, that just wouldn't occur like that, basically, if it's one group. Or it's less likely. Oh.
Like, if I flip a coin 100 times, what's the chance I'll get, 99 heads in a row? Well, it could happen, but it'd be very unlikely, right? So it'd be very unlikely that I could have ended up in a situation like this on the left if it was the null hypothesis. Those groups were being taken randomly from the same normal distribution.
So it's just protected.
Yeah, on the right, what's the chance that could have happened? Well, I would say it's much higher because, look how much they overlap.
Yeah.
So it only takes a couple of values that are really high or really low.
Oh, yeah, I see.
To shift the average value, right?
Yeah. You could even look at, if you cut off the bottom of the y-axis and the top of it, a lot of the data literally is from the same section, right?
That's right. Yeah, exactly.
Okay.
Yeah, that's a really good way of thinking about it. How many data points would you have to shave off from the top and the bottom for this to just look like everything was the same?
Yeah, okay.
Whereas on the left, you couldn't really shave. No matter what you did, they're not even overlapping, right?
Yeah, okay.
So the chance of that happening, if the null hypothesis was true, would be pretty small.
Yeah.
And that's what the p-value says. The p-value on the left might be 0.0001, right? 1 in 10,000, or even lower, 1 in a million. Whereas the p-value on the right might say, well, that could happen 10% of the time, 0.1. So that kind of logic of sampling and a null hypothesis and one distribution and the probability of this happening, all of that is the same kind of conceptual framework for a t-test, for an f-test, for a chi-square, or all of the flavors of ANOVA.
Okay.
It's all the same kind of concept in null hypothesis statistics.
Do they all, I know ANOVA is assuming, you either have multiple groups or one distribution.
Yeah, that's
with the normal test, is it assuming a single distribution?
Yep.
Okay.
Yeah.
And is it, So I've taken a few stats class now, but this is a general knowledge question. I probably should know, but like, do we actually assume data in general is normally curved? Like, because I know there's different tests for it in different places, and sometimes you seem to care, sometimes you don't.
Yeah, it's a really good question. I think the pragmatic answer is that, yeah, usually we assume that the data we collect are normally distributed.
Okay, wow.
And usually for these tests, like we've seen in class, you're supposed to test that assumption, right? You're supposed to verify that it looks true.
Yeah.
The reality out there when people are doing experiments is quite often people just ignore that test and say, I don't want to deal with this. I just want to assume, pretend it's okay.
Yeah.
But we know that there are some quantities, some variables out there in the world that are not normally distributed.
Okay.
Like, for example...
like income is one, right?
Yeah, yes.
Yeah.
Yeah, income. Reaction times. If you collect reaction times in any kind of experiments in psychology, reaction times are not normally distributed.
Oh, that's so interesting.
Yeah,
okay.
They're kind of normal-ish on the low end, on the fast part, but there's a long tail of reaction times. So we know reaction times are skewed to the right.
Okay.
So any test we do that involves reaction times, you have to deal with non-normality somehow.
Okay, so it's more kind of a base assumption, but then if you know it's an issue, you really
there are some variables out there that everyone knows is not normally distributed. But yeah, it's kind of a bit, if you don't know that, and no one can tell you when you ask them, is it? And everyone says, I don't know.
Yeah.
And then you kind of assume that it is, but you test.
Okay.
Assumption. Yeah.
Okay, so that makes sense.
Yeah.
Okay. So it's always to do with variability when it comes to these tests, in a sense, and you want...
Yeah. There's sort of three aspects that I think of that all sort of trade off each other.
Sure.
One is the difference in the means that you see in your sample.
Okay.
That's one aspect. The second is the variability within each group, right? We've talked about those two already.
Yeah.
And the third is the number of observations.
Oh, yeah. And higher is always better, right?
Yeah.
Okay.
So, exactly. Higher number, more data always gives you more confidence that the sample you have is a true reflection of the population.
Well, and it technically is more of the population, so...
Well, yeah. No, that's a good point. It is more of the population.
Yeah.
Yeah.
Okay.
So if you have the same difference between means and the same variability, but in one case you have a huge amount of data and in one case you have only a little amount of data, then the huge amount of data version of this is the one where you're going to have more confidence that what you see in your sample is real and not just random sampling error. Okay. Yeah. So on this plot on the right, I don't know how many data points are actually here, maybe 15 or something. If you had 1,000 data points in each of these three groups, and the variability was still that big, then your p-value might actually tell you, well, you know what? It might be a small difference between means relative to the variability, but because I have so much data, I'm confident this couldn't have happened randomly.
And now, but would that be significant? And that's the weird with the word significance, right?
That relates to that. Yes, that relates to what we talked about briefly about effect size and the word significance. Yeah. So like I said in class, I like to use the phrase statistically reliable.
And I like that, and I hadn't heard that before. And I was trying to parse out the other day when you use it that way and when you use it the other day, and I think I just got lost.
Yeah, I think just the way it's been taught for decades, and so the way most people phrase it is, it's statistically significant, but statistically significant, right? And it's a subtlety, when a scientist or a statistician says statistically significant, what they actually mean is statistically reliable. Okay. The trouble is when a journalist or a layperson hears statistically significant, they think, oh, it's like actually important.
Yeah.
Significant in the usual use of the word. And it might not be. It might just be a teeny tiny difference that you have a lot of confidence is real, right?
Yeah.
It's tiny.
And then what would you call that? What would you call that then? Like, if one is statistically reliable, what is the other one? Like, a big deal? But okay.
Yeah. Well, yeah. So you can have something that's statistically reliable and unimportant.
Yeah.
And you can have statistically reliable and I don't know what I mean.
Important.
It really consequential.
Yeah. Oh, I like that.
Like I want to say significant, right? But that's going to confuse.
It is. Yeah.
Consequential or yeah, that's a good one. I like that one.
Yeah, I like that too. Because you couldn't even argue like novel would be a fun way to say it, but you couldn't argue it's new. So yeah, I like consequential.
Yeah. And something can be novel and still tiny.
Oh, that's a good point.
Yeah. You know what a good example is? A lot of the literature in psychology on sex differences of various kinds. They turn out to be statistically reliable, but oftentimes very small.
Oh, and I bet that's not reported because I'm actually really interested in gender, so I'll usually look that up for my psychology classes, and that's never really talked about.
Yeah, so when you read stuff in the sort of popular press about sex or gender differences,
yeah,
I don't know, like spatial cognition and who knows what else, that they'll talk about highly significant results, highly significant differences, and they're actually referring to highly statistically reliable differences because often these studies have really big sample sizes, like 10,000 people.
Yeah. Okay.
But when you look at the sort of two normal distributions corresponding to whatever male and female, men and women, they're almost completely overlapping. One is like slightly shifted over.
Wow, that's wild. That's like pretty inappropriate. That's not.
It is. Yeah, I mean, I think in our culture we've in some cases constructed all these assumptions and stories around sex and gender differences that come from these things that are actually
I'm
particularly consequential.
Yeah, I'm actually I might do my English master's next year, and I'm going to do it on that because that's very interesting.
Yeah, that would be very interesting.
Yeah.
I mean, it's very interesting. It's also a little disturbing.
Oh, it's super
In some
disturbing.
cases, stuff like educational policy for schools and the way teachers think about like math, for example, and when they're teaching little kids, this can have real consequences.
Oh, absolutely. It's pretty wild. Yeah. No, it's interesting now, too, that more women are in university, so, like, it's kind of shifted in a weird direction, too. Now it sounds like men are represented, and that's kind of, we don't want that either. Yeah, no, it's a weird time with gender stuff.
Yeah, I was just reading something, in our psychology program here, in the undergraduate program, women outnumber men by it's like 60-40 or something.
I believe it. And the English classes are all women. Like, it's like a male professor and then like all female.
Where are the guys?
Yeah.
Maybe they're all doing engineering or something.
Yeah, no, but it's sad though. You don't like to see that because then people aren't living up to the potential of whatever their abilities are, right?
Yeah, for sure.
Yeah.
All right. Well, we got just a couple minutes.
Oh, I know. I shouldn't be chatting. It's just interesting. Okay, let me see. Let me see if I have a burning question. Let me just scroll through really quick what I read on my phone. Okay, because I'm kind of just slow and like math is like laborious for me right now because my brain is not wired to do math, right? Do you have any tips for me? Like last semester I had to take a data science course, so like I just had to practice a lot of math, right? Which I hadn't done for like a decade. But so like with this, like can I do something weird to practice that might help me?
I think the right answer to that is on the exams you're really not going to find math. I'm not going to ask you to calculate things.
Yeah.
There might be equations that you have to recognize.
Yeah.
Like which of the following is an equation for whatever, and then I'll give 4 equations. That's more like of a memory thing. That's sort of
okay.
being able to say, oh yeah, no, that's the one that he showed. That's the equation for. I don't know what it was.
Yeah.
Something about logistic regression.
Definitely. I guess maybe the short answer too, like, because people can be very, very educated in how to speak about math, and I am just not up to date on it anymore. Like, if I basically say, like, what you said and, like, anything related to it in the textbooks, is that, like, good enough, or does it have to be, like, really good? Like,
no.
Okay.
That's good enough. Yeah, that's good enough.
Okay, and I guess the other question would be, like, the theory about the logistical regression. You really went into it, and it was so great, but I don't think I could recapitulate that, like, very easily.
Yeah, you know what? Me either.
Yeah, it's a lot. It was cool. It's cool.
Yeah, it's cool and it's important, but it is a little bit, sort of, it suddenly goes a little bit deep in the other area, right, compared to the other material, which is all kind of swimming around the same neighborhood. So
Yeah.
I acknowledge that. It might be a little bit challenging. I think focus on the slides.
Okay.
And I would say do the reading again. Read the readings again.
Yeah.
But when you're doing the readings, try to, and this applies to all statistics, I think. Whatever textbook or course you're reading from in statistics, whatever topic it is, when you read a chapter in a stats textbook, there's kind of like, think about it in terms of levels of complexity.
Okay.
There's like the top level, which is sort of like, what is this and why are we doing it? And like, in general, how does it work?
Yeah.
Right? Get a hold on that first, and then even like reread the chapter with an aim of like, okay, what's the next level of detail that I need to know? Okay. So this is generally why we're doing it, and generally how it works. So how does it actually work? Like, what is the logistic regression equation look like?
Yeah.
Right. That does it, and how do we take that equation and predict value? And then there's always a third level and a fourth level, and you can go down the rabbit hole as far as right.
Yeah.
Chapter will sort of point to other materials and say, for more information about this, read that.
And I feel like a lot of chapters will tunnel down like very quickly into like R code or into something tangential, and it's hard for me to understand, like, do I pull out or do I really like figure that out? So like you're saying the overview is okay.
I think pull out, right? My suggestion and my approach, which it took me many courses to sort of figure out how to do it. My approach is to read a chapter several times with different aims each time.
Okay.
Instead of the very first, like, if you try to read a stats chapter, and the very first time you read it, you sort of go down every rabbit hole and come back up, and go down every rabbit hole and come back up. Oh man, unless you're like, a stats sort of aficionado, that's really hard.
I don't have enough caffeine for that, I don't think.
I say, like, read it first.
Yeah.
Don't go down the rabbit hole. Just get a top level kind of view.
Okay.
And then, take a break.
Yeah.
Go for a walk. Read it a second time. And go down sort of one step each time.
Okay, I can do that.
And when you do that, that also gives you a chance to review the top level, make sure you understand it.
Because every time you need to build on it. Yeah. Okay.
And if you think you need to, take another break, even save it for the next day, and read it a third time and see if there's another level that seems important. But I think for this course, I would say like 2 levels down. Okay. The top level and 1 more level, and you're going to be in great shape.
Okay, awesome. Thank you. That helps so much. That makes you feel a lot more confident just about what to expect and like what is happening. Because like I take English course, I like know what to expect, right? Like I have it all like worked out. I have a plan. It's so beautiful. But then it's when you're doing something different, it's hard. So thank you. I will take your strategy and I will use it. Okay. Awesome.
If you have other questions, just shoot me an email.
Okay, I hope the rest of your break is good. Thank you for taking this time. I really appreciate it.
Yep, okay.
Bye.
Bye.